reaction? Initial flow rate times the heat capacity. And now we need to solve these two things simultaneously in Excel.
We're going to need to, like, in a way, plug in for rate of A constantly, right?
Yeah, but you could just, I mean, you know what the rate of A is in terms of conversion and temperature. I mean, the rate, just remember that the rate is everything that's up here except this. So I just didn't want to write it twice. Right? And when we do it in Excel, you can just set up the rate as its own column if you prefer to do that. And then rather than using this form in Excel, you can just use this form. But yeah, that's why you don't see things that you're used to seeing down here like conversion, is just because we've just left the rate as the rate. Any other questions? Okay, so if we're doing this in Excel, what is the Euler approximation of this differential?
T1 minus T0.
Yeah, I mean, I like doing T2 minus T1 just because we already have sort of a T naught, but yeah. So it's some change in temperature divided by some change in weight of the catalyst. And up here, same thing. And if you like, you can define this in your Excel spreadsheet, right? So that's what we did when we set up ours. That's how the other one was set up too. Is delta V was set up as a cell. And so then this just becomes everything on the right-hand side. T2 is equal to the right-hand side plus, we'll do it for this one up here. Well, we'll do it for this one because it's so simple. So x2 is equal to x1 plus delta weight times negative RA over FA naught. That's it. So you guys can type all of that into Excel without much difficulty. For any time that you need to put in a conversion, you use x1 or t1, right? You use the row above you, not the row that you're on. Otherwise, Excel is going to tell you about a circular reference. Well, you really can't use the one you're on, I guess. Anyway. Any questions? Okay. Yes.
You asked us to remind you that you wanted to just draw with CP that's not equal to 0, right?
Yeah, that's a good point. I'll pull it up. Yeah, we'll pull it up now just real quick. Oh no, I can't, sorry. I just didn't put in the energy balance for that case. So the energy balance is already assuming that delta CP is equal to 0. Okay, so here's the PFR with heat exchange. So what are the differences? Now I'm doing this in terms of weight. Here's conversion. I did put in the rate. I find it easier at some point to just have the rate as its own column. Temperature, rate constant, and then 1 over the rate so that again we can look at Levenspiel. Here's the inlet, so the stoichiometries. The thetas, that should be 0. CP, and then instead of just putting in the delta H, I just cheated and I used the table, but this isn't actually correct. This is just what you needed to put in order to get a delta H equal to what we got, which is negative 20,000. So anyways, we're also given the initial concentration, we're given the initial flow rate, we're given the inlet temperature, inlet conversion is 0, delta CP is 0, delta H reaction minus negative 20 kilojoules per mole. Inlet CP is just the heat capacity of A, because there's only one stream in my inlet. So that is, again, that is the theta, it's the summation of theta times heat capacity. The cooling temperature, the cooling fluid temperature is constant. We were told that, and it's 300. And then this we were given, what was the value here, 5? And then epsilon is equal to 1, like we said. And again, this is just how quickly am I changing the weight of the catalyst on my spreadsheet, 0.1. But again, that's not given by the problem. That's just a parameter I can change to either make my spreadsheet longer, shorter. And if it's too large, then I'll get some very bad numbers. But usually it's pretty obvious. Okay, so what do we expect? Is this an exothermic or an endothermic reaction? Exothermic. So what's going to happen to the temperature along the bed of the reactor? Yeah, but now I'm cooling it with something at 300, way colder than our inlet temperature. Our inlet temperature is 450. My cooling fluid is 300. So you think it'll go down first and then go back up. But it could also go up and then back down. Which one wins, right? How do we know? What's ultimately going to determine whether the temperature initially drops or initially increases? It's a competition between the rate of the reaction times the delta H of reaction. That's generating heat, right, in this case, because it's an exothermic reaction. And now on the other side of that equation, we're removing heat. I think the projector light will actually help us here. So here we're generating heat. Here we're removing heat. So it also depends on what is my delta T, right? But also my overall heat transfer coefficient, the contact area, the density of my solid, all of that also plays a role. And then, of course, this is the resistance. Hopefully you guys have learned by now that everything in chemical engineering is driving force divided by resistance. God, I hope so. So this is our resistance, right? This is the heat capacity of our fluid. How quickly do I change its temperature depends upon its heat capacity. So that's our resistance term. All right, so let's look at it. Okay, so this is conversion versus weight of catalyst. Increases and then hits a constant value of 1 because it's an irreversible reaction. Here is the temperature versus weight of catalyst. So along the length of the reactor, we get an increase in temperature and then a slow decrease. So it's exothermic, and at least at first, we're not removing heat fast enough. But what happens when the conversion hits 0? At that point, how much heat are we generating? Sorry, when the conversion hits 1. How much heat are we generating? None. So, in that regime, we're simply cooling it down. We've stopped generating heat. So, of course, any amount of heat that we're removing is going to cool down the reactor. And you see that if I lay these over top of each other, it really is, you have to get all the way to a conversion of 1 before the cooling actually has much of an effect. Yeah?
Will it eventually go down to reach 300?
Yes. Yeah. Once we hit 300, we can no longer cool. The driving force, the entire numerator, right? That's our driving force. The conversion is constant, so the rate is 0. And that was rate times delta H of reaction, so that term goes away. And then the first term has TA minus T. So if those temperatures are the same, the driving force for the entire process is 0. Okay, so what would happen if I changed the heat transfer coefficient? happens if I set this to 0? How are these curves going to change? What's going to go up? We have two curves. So first, which curve are you talking about? The temperature curve. So the temperature curve is going to do what? It's never going to decrease. That's correct. If I set that to 0, I'm essentially running this adiabatically, right? That's the exact same as an adiabatic reaction. So this is going to go up, and it's going to be constant at some temperature corresponding to 100% conversion. Is it going to increase faster or slower? Faster. What about the conversion? Is it yeah, go ahead.
What was the graph that was the straight line? Heat capacity versus, or temperature?
That's conversion versus temperature.
Is that this one? That's not this one.
No. And that was for an adiabatic reactor.
Yeah, so
It's
what does
not
it
going to be
look
the
like
same
for
here.
this?
We'll plot. What's going to happen to the conversion as I change this from cooling to adiabatic? If I change the heat transfer coefficient, that whole lump term from 5 to 0. It's going to get there a little bit faster, right? This line's going to shift to the left. All right, so let's do that. Let's just see. Good. So if you guys can think through this stuff now, this is the type of thing that you got to be able to think through on a test. These conceptualized questions of what happens. You know, this test isn't about, I don't care if you guys know how to figure out what volume reactor will get you 85% conversion. If you go work someplace and they have a reactor, they already have software they expect you to use. But if you don't know that you want to operate an exothermic reactor with a PFR, or you don't know what general types of things are going to happen, that's what scares me. Especially when we talk about the next topic, which is multiple steady states, and that's how reactors blow up. All right, so this was at 5. What happens if we make it